Welcome to the course analysis of several variables, and this is the module 3 part 1 where we are going to discuss about the differentiability of several variable functions. So the this chapter have this module have two section. One is the first one is the differentiability, and the second one is the chain rule. Differentiability of several variable function is defined as follows. So for first we will take that omega be an open ball on Rn, and then let's A belongs to a point in the omega, and where we are going to define the differentiability of the function, and f is a function from omega to Rm. Then the differentiability of this function f is defined as follows. Let's say f is differentiable at the point x is equal to a if there exists one function epsilon from b0 r to rm and a linear mapping a from Rn to Rm. So here b0r is open ball center at 0 and radius and there exists a linear mapping A from Rn to Rm such that f of a plus h is the function f a plus h can be re-expressed as f of a h absolute value of h epsilon h. And if we can write that and we follow these conditions, that epsilon h will tends to 0 when h is tends to 0, or some cases we write absolute value of h tends to 0. Then this functions f will be differentiable. So we need, okay, now we try to give few notes about these notations. The first thing is that we are saying that f of a plus h will be expressed in that form in the previous slide. But the first question arises that is f of a plus h is well defined. So let's see that. Now if a belongs to omega and the set omega is open, so then by definition there exists a ball center at a with radius r such that x belongs to Rn and mod of x minus a less than r. This is a subset of omega by the definitions of the openness of omega. So this set, this ball should be belongs to the set omega. Now let h belongs to be 0r, as we say that we need that h. Then absolute value of h we can write it as a plus h minus a. Just add a and minus, which is less than r, because h belongs to b0r. So what does it mean? By the same definitions we can see that a plus h belongs to the ball bar. So therefore f of a plus h is well defined because it belongs to omega. The point a plus h belongs to set omega, so therefore a plus h is, so therefore the function f a plus h is well defined. Okay, now if a belongs to linear from Rn to Rm and epsilon h tends to 0 as h tends to 0. Now if a is linear from Rn to Rm exists, then it is unique. Okay. So there is only one linear functions is from Rn to Rm if it is exist, and that linear functions is actually will gives you the derivative of the functions at the point A. It will be same as the functions derivative in the point. Now if it is differentiable, f is differentiable on omega if it is a differentiable at every x belongs to omega. So we defined before that is only a particular point A. Now it is for all point at the omega. Then the new functions means f dash will be a functions from A and linear Rn to Rm, means the domain of this range for this linear functions will be the range of the function, and that is defined as x is a functions f dash. Okay, so this is about the few facts on the differentiability of functions. Now we have an examples here that prove that f Rn to R is defined by fx equal absolute value of x whole square. X dot x is differentiable on Rn, and we need to find f dash x. Solution. So let h belongs to Rn, then f of x plus h, this is equal x plus h. The distributive properties of the dot product, we can write it here, x dot x plus x dot h plus h dot x plus h dot h. So this is equal x dot x, which is the given function fx, plus x dot h, so we can write it to x dot h plus h dot h, which is absolute value of h whole square. So this is equal f of x plus a h plus absolute value of h epsilon h. So where ah is equal to x dot h and epsilon h is equal absolute value of h, because this absolute value of h whole square we separate it as per our requirement, absolute value h multiply epsilon h, so epsilon h is equal absolute value of h. Clearly epsilon h is equal absolute value of h tends to 0 as absolute value h tends to 0. So this condition is satisfied. Now we are left with that AH is linear. So next we'll show that AH is linear. So AH is equal to x dot h. So let's h1, h2 belongs to Rn and alpha belongs to R. Then A h1 plus alpha h2. So this is by definition it will be 2 x dot h1 plus alpha h2. Now again, by the distributive properties of the dot product, we can write it here 2x dot h1 plus alpha x dot h2. So this is equal to x dot h1 plus 2 alpha x dot h2. So which is, this is together we define as a h1 plus alpha a h2. So this implies a is linear. Okay, now this question asks that find f dash x. So we will find this f dash x after some slide. But we'll note it here that it will be this 2a x dot h because of this remark. This one. Because of this one, so we can say that f dash ah is equal this 2x dot h. Okay, now we have a theorem here, and which is a general theorem and true for any differentiable function, that if it is a open ball on Rn and a belongs to omega and this function is defined, then f is differentiable at a, then it is continuous. So this is like the calculus 1 single variable function, that every differentiable function is continuous. So this is also that same conditions, that every differentiable function is continuous on Rn. Okay, this is another criteria for the differentiability of function, constant function. So okay, so this theorem gives us the differentiability of a constant function. So if f is differentiable on omega and for every x belongs to omega, f dash x is equal 0. So 0 is a 0 functions from Rn to Rm. That means h from Rn will goes to 0 of Rm. So to be specified, we can, this is 0 of Rn will goes to 0 of Rm when f is a constant function. Now here is another interesting characteristics, that every linear function. So this is the condition that function should be linear. If function is linear, then f is differentiable on Rn, and for all x belongs to Rn, f dash x is equal f. The functions have the same derivative. The linear functions derivative will be same as the function. So how this part, to understand it, we will take one example. Okay. Let f is from Rn to Rm, defined as fx is equal a dot x for some fix a belongs to Rn. Now from here we have that it can be shows that, okay, we can show easily that f is linear. You can just take fx plus lambda y and the distributive properties of the dot product, these functions will be linear. Okay, now so therefore by this theorem, so by this theorem we have f dash x on h is equal f of h. So since f dash is a function from Rn to Rm, so we take one h belongs to, so for all h belongs to R. So this is equal a dot h. Okay, so now we have another interesting definitions of the function. So it says that let omega be an open ball in Rn as usual in R. So here is the function is from R and f is from omega to Rm. Then f is differentiable at A if and only if fi I is from 1 to m are differentiable at A and f dash A is from R to Rm defined as f dash h f dash A. So here is the interesting part is that how to, so let's explain this theorem. So f is here omega which is subset of R to Rm. So therefore here is t is single variable and this is will be f of t. So f of t will be, because it is on Rm, so you will have here f1t, f2t, fmt. The m component will be there. So this f is differentiable if each f1, f2, fm are differentiable, and the function f dash a will be, so f dash a is equal f1 a, f1 dash a, f2 dash a, and fm dash a. So this is the general definitions, but since it is a function, so we have to take this function on operating on h, then in this case it will be multiplied by h. So let's have one simple example. f of x, f of x is defined as, let x cosine x and e to the power x square. So in this case, note that the function is from f r to r2. So the function is differentiable if each of this component is differentiable. So this is differentiable, this is differentiable. So f is differentiable at any x belongs to R as x cosine x and e to the power x square are differentiable. So therefore, and f dash x operating on h is equal the derivative of the first component, which is cosine x plus cosine x minus x sine x minus x sine x multiply h and 2x e to the power x square